this lecture is today I will see convergence test of series. In my previous lecture, I had seen geometric series test, P series test, divergence series test, comparison test, limit comparison test, ratio test, root test, absolute value test, alternative test. Those convergence test of series I had seen in my previous video. But in my previous video, I did not see the integral test of series. Today I will see integral test of series at first. Then I will see various type of example based on these tests. Test of series. This is actually nice test. Two valued is a series is convergent or divergent. The statement of integral test of series is f(x) is continuous positive and decreasing function for x greater than equal to 1, and let ak equal to fk, and this is true for k equal to 1, 2, 3, so on. Then series k equal to 1 to infinity ak and integration 1 to infinity, in which value here given integration 1 to infinity, here ak means fx dx, either both converges or diverges. As for example, consider the series n equal to 1 to infinity 1 over n square. We all of us know this series is convergent series, but here I will use the integral test. Consider an equal to 1 over n square. Since here I will use the integral test, so fn equal to 1 over n square, and here the interval is 1 to close to 1 to open infinity. Therefore fx equal to 1 over x square here. To evaluate integral test, which is obviously positive and continuous function, and since x1 less than x2, then obviously x1 square less than x2 square, then 1 over x1 square greater than 1 over x2 square, that imply fx1 greater than fx2, and f prime x equal to obviously minus 2 over x cube, and in the interval close to 1 open infinity, f prime x always less than 0. That means our given function fx equal to 1 over x square, this is decreasing on the interval close to 1 open infinity. That means this function is positive, continuous and decreasing function. Okay. Now we can apply the integral test in better way. The integral test is, since the interval is close to 1 open infinity, that means 1 to infinity 1 over x squared dx. And we all of us know this improper integral when 1 over x squared, when x lies from 1 to infinity, this improper integral is converges when p greater than 1. Here p equal to 2, which is obviously greater than 1. So integration 1 to infinity, this improper integral always convergent. We all of us know, in my previous video I have seen this type of improper integral elaborately. Next example, series 1 over n log n. At first I will use here limit comparison test. For limit comparison test, consider bn equal to 1 over n. Then limit n tends to infinity 1 over n log n over 1 over n equal to limit n tends to infinity 1 over log n, and limit n tends to infinity 1 over log n equal to 0. Since this value is 0, therefore we cannot conclude either convergence or divergence by limit comparison test. Okay. Now I will apply integral test. For integral test, here integration 2 to infinity fx means 1 over x log x dx. Obviously, fx equal to 1 over x log x, this is greater than equal to 0 for all x greater than equal to 2. That means for all x greater than equal to 2, fx greater than equal to 0, that means this is positive function. Okay. Also this function is decreasing function because x log x is increasing function. So 1 over x log x obviously would be decreasing function. Therefore, we can apply integral test. 2 to infinity 1 over x log x dx. And since this is the improper integral and discontinuity at the point infinity, so this improper integral would be such type limit b goes to infinity, integration 2 to b 1 over x log x dx. Now consider u equal to log x, then 1 over u equal to 1 over x dx, then the improper integral would be such type limit b goes to infinity, integration 2 to b 1 over u du, which is equal to log x. Here the limit b to 2 to b. Therefore, limit b goes to infinity, this value would be log b minus log 2. And obviously, after evaluating the limit, this value would be infinity. Obviously, we can tell this improper integral is divergent. And since this improper integral is divergent, that means this series is divergent series. Now I will say convergence test of two series. Series n equal to 1 to infinity n square e to the power minus n, and series n equal to 1 to infinity n square e to the power minus n cube. For this series, we all of us know, for this series we can apply ratio test, and by ratio test, here n equal to n square e to the power minus n, then limit n goes to infinity, n plus, by ratio test this is n plus 1 over n, that means n plus 1 whole square e to the power n plus 1 times e to the power n over n square, and this value would be limit n goes to infinity n plus 1 whole square. Here cancel e to the power n e times n square, and this value would be 1. Therefore, this is equal to 1 over e, and 1 over e always less than 1, since limit n goes to infinity n plus 1 over n less than 1, then by ratio test we can tell this series is convergent series. This is we can tell by ratio test. But second series is series n square e to the power minus n cube. For n cube, here we cannot apply ratio test. Here I will use integral test for series. For this series, by here we can apply integral test because fx equal to this and this is positive. Since here n equal to 1 to infinity, this is positive for all n greater than equal to 1. Also, this is continuous function and decreasing for all n greater than equal to 1. Therefore, we can apply integral test of series. Here limit would be integration 1 to infinity, and this value would be limit b goes to infinity integration 1 to b x square e to the power minus x cube dx. then this value limit b goes to infinity 1/3 1 to b 3x square e to the power minus x cube dx, and evaluating this value would be 1 minus 1/3 1 over e to the power b cube plus 1 over 3e, and as limit b goes to infinity, this value would be 0. That means this value is 1 over 3e, and this is obviously finite value. Since this value is finite value, so we can tell this improper integral is convergent. And since this improper integral is convergent, that means this series is convergent series. I hope my all viewers have understood integral test of series in better way. Now I will discuss convergence test of this series as just a review. First I will discuss some example of ratio test. First example, series n plus 5 over 5 to the power n. Obviously this is an, and ratio test is limit n tends to infinity a n plus 1 over n if this value is L and L less than 1, then we can tell by ratio test the series is convergent. But if L greater than 1, then we cannot tell by ratio test the series is convergent. Okay? n plus 1 over n, that means limit n tends to infinity n plus 6 over 5 to the power n plus 1 times 5 to the power n over n plus 5, and this equal to limit n tends to infinity n plus 6 over 5 times n plus 5, and after evaluating this limit, this value would be 1 over 5, which is less than 1. Therefore, since the value of the limit less than 1, therefore by ratio test we can tell this series is convergent. Our second example of ratio test is this. Notice in which series we can apply ratio test. This is big matter here. This type of series, a to the power n, power of a, factorial, we can apply ratio test. For this power 5 to the power n, here I have applied ratio test. Here notice power 3 to the power n, another power n square, here n factorial. So here also I will apply ratio test. n plus 1 over n is this, then limit n goes to infinity a n plus 1 over n equal to this, and after calculation this value would be limit n goes to infinity 3 times n plus 1 whole square over n square times n plus 1, and putting the limit this value would be 0, which is less than 1. Therefore, since this value is less than 1, so by ratio test we can tell this series is convergent. Okay. Next I will see root test. In which series root test will applicable? This is now I will see. Just as a review, root test is series an and limit n tends to infinity if an to the power 1 over n equal to L, and if L less than 1, then we can tell this series is convergent, and if L greater than 1, then we can tell this series is divergent. Then notice this type of series. In this type of series we can apply root test. At first notice this example. Notice the quality of the series in which we can apply root test. Now notice the series for first series, this is the an. Here I will apply root test. Limit n tends to infinity n to the n power 1 over n. This is equal to limit n tends to infinity 3n plus 1 over 2n to the power n times 1 over n. Then this is equal to 3n plus 1 over 2n, and this value is apply the limit, then this value equal to half, and since half less than 1, therefore by root test we can tell this series is convergent. Second, notice this series here n equal to this, n to the power 1 over n would be this. Now limit n tends to infinity a to the power 1 over n equal to 1 over e, and this value is less than 1. So this series also convergent. Third, this series here n equal to this, then n to the power 1 over n would be this value, the value of limit n tends to infinity n to the power 1 over n. After putting the limit, this value would be 8 to the power 1 over n means 1, and this value is 3, then 1 over 3 always less than 1. Therefore, this series is convergent. Next, notice this series. Here we can also apply root test. Here n equal to this, then n to the power 1 over n would be this. After calculating, this value would be 1 over n to the power 1 plus 1 over n. Then apply limit both sides, then this value would be 1 over n, and evaluating this limit, this value would be 0, which is less than 1. Since this value is less than 1, therefore obviously this series is convergent. Okay, now I will see in which series comparison test would be applicable. First, consider this series. For this series, n square plus n, always this is greater than n square. So 1 over n square plus n always less than 1 over n square. By this inequality, series 1 over n square plus n less than series 1 over n square. And since this series is convergent series, therefore by comparison test, this series is convergent. Our second series is this. We all of us know cos square n less than equal to 1. Therefore, n plus n square cos, here not n square, here n. N plus n cos square n less than equal to n plus n, which is less than equal to 2n. Therefore 1 over n plus n cos square n greater than equal to 1 over 2n. Here therefore we can apply this series here series. Since this series is divergent, so by limit comparison test we can apply our bigger series also divergent. Our next series is log n over n. When limit n goes to infinity, we all of us know n approaches faster than log n, and log n always greater than equal to 1 for all n greater than equal to 3. Therefore, log n over n is greater than equal to 1 over n. Okay. Then series log n over n greater than equal to series 1 over n, and since this series 1 over n is divergent series, therefore by comparison test our bigger series is divergent. I hope my all viewers have understood in which type of series test we can apply comparison test. Now I will see in which test I will apply limit comparison test. Notice these two series. Here I will apply limit comparison test. Now I will see some example of limit comparison test. I will see in which series I will apply limit comparison test. Actually, limit comparison test is most powerful than the comparison test. We all of us know limit comparison test. Limit comparison test is series AN compared with the series BN, and if limit n goes to infinity, AN over BN equal to C, which is greater than 0. And if the series BN convergent, then always that imply the series AN is convergent. Okay. Now our given these two series. First, compare this series as a here n square, compare which is equal to 1 over n. Compare this series as a 1 over n, and then limit n goes to infinity. Consider this is an, this term is an, and this term is bn. Then limit n goes to infinity, n over bn equal to, apply the limit, this value would be 1. Since the series 1 over n is divergent, then our given series is also divergent. Okay. For our next series, obviously this is an, and rearrange an is such type because we all of us know limit n goes to infinity 1 plus 1, limit n goes to infinity 1 plus 1 over n to the power on equal to e, and this value is finite value. So I have arranged this n as this type. Then consider bn equal to just 1 over n to the power 3 over 2. Then limit n tends to infinity, an over bn would be, obviously this value would be, just cancel this part, this value would be e, which is finite number. Okay, I hope my all viewers have understood this is. And since bn, the series bn means obviously the series 1 over n to the power 3 over 2, which is obviously convergent because here p greater than 1. Since bn convergent, then that imply obviously our given series A, this series is convergent. Okay. Next, notice this series, and we all of us know tan 1 over n means 1 over n plus 1 over 3n cube plus so on times here 1 over square root of n. Consider this is as a n. Then bn would be, compare this an versus bn where bn equal to, just common 1 over n from this series, 1 over n plus 1, that means this is half. This means bn, consider bn equal to 1 over n to the power 3 over 2. Then this is n, this whole term. Then limit n tends to infinity, n over bn equal to 1, which is finite number. And since the series bn is compared as the series 1 over n to the power p, where p, here p greater than 1, since this series is convergent, therefore our given series is convergent. This is we can tell by limit comparison test. Now consider this series. Here I will apply both tests, comparison test and limit comparison test. By comparison test, this term less than equal to 1 over n square plus 4n. Therefore, this series less than equal to 1 over n square plus 4n. and this series is convergent series by limit comparison test, because here n equal to this and consider bn equal to 1 over n square, and an over bn would be finite number, and since the series 1 over n square is convergent, because this is the p series, here p equal to 2 which is greater than 1, therefore our given series, this is convergent by limit comparison test. Since this series is convergent series, therefore our given series, actual given series is convergent. I hope my all viewers have understood in which type of series we can apply limit comparison test and comparison test. Second, notice this series. Here fx equal to 1 over x times square root of log x. Obviously this type of function continuous, positive and decreasing. Therefore we can apply here integral test. By integral test, integration 2 to infinity 1 over x times log x minus half. After integrating, this value would be, since here infinity, b goes to infinity, here after integrating this value would be 2 log square root of log x, and here the integration 2 to b. Now evaluate this limit, then this value would be limit b goes to infinity 2 square root of log b minus log square root of log 2, and this value would be infinity after putting the limit. Since this value is infinity, so by integral test we can tell this series is divergent series. Okay? But if we consider this series, obviously this term here alternate. Here n equal to 1 over n log n, which is decreasing sequence, and limit n goes to infinity, 1 over n log n is equal to 0. For since this sequence is decreasing sequence and limit n goes to infinity, this sequence tends to 0. Therefore by Leibniz test we can tell this series is converges absolutely. Because in my previous video I have defined what is the Leibniz test. Similarly, I will say another example of Leibniz test. Our next given series is this series. Here also I will apply Leibniz test. Consider n equal to n over n square plus 25. We have to show at first for Leibniz test this sequence is decreasing sequence, and to find decreasing, consider fx equal to x over x square plus 25, and notice f prime x equal to this and f prime x less than 0, strictly less than 0 for x greater than 5. Therefore obviously fx is decreasing. That means since an, this sequence is decreasing sequence and limit n goes to infinity, an equal to 0, therefore the series is converges by Leibniz test, because this sequence is decreasing sequence and limit n goes to infinity, n tends to 0. Therefore by Leibniz test we can tell this series is convergent series by Leibniz test. I hope my all viewers have understood clearly in which type of series Leibniz test would be applicable. Now I will see one nice example in which comparison test and integral test will applicable both. This example is this series. For short calculation, at first I will here use comparison test, because notice here n plus 1 whole cube. We all of us know n plus 1 whole cube always greater than n cube. Then 1 over n plus 1 whole cube always less than 1 over n cube. Since here in the question the series given n over n plus 1 whole cube, therefore multiply both inequality by n. N over n plus 1 whole cube less than n over n cube. From this it implies 1 over n square. Now multiply this inequality by log n, because here n log n over n plus 1 whole cube. N log n over n plus 1 whole cube less than log n over n square. Now apply series sign in both sides. Now by comparison test, if we can to apply this series is convergent, then obviously by comparison test we can tell this series is convergent. To evaluate this series is convergent, consider fx equal to log x over x square. Obviously this is continuous, positive and decreasing for all x greater than equal to 2. Integration log x over x square. We all of us know this is equal to minus log x over x minus 1 over x. And since here the integration n equal to 1 to infinity, integration 1 to infinity log x over x square equal to limit b goes to infinity minus log x over x minus 1 over x. Here the limiting value 1 to capital B. Now after putting the limit, I will get the value is 1, and since the value is finite, so the series log n over n square converges by integral test, and since this series is converges by integral test, therefore by comparison test our given original series is actually convergent series. Okay, next example I will see this series. Is this series is convergent or divergent? Here also I will apply the comparison test. Log n to the power log n, this value always greater than n square. And here the integration for n equal to 2 to infinity. For this, apply log both sides, then log n to the power log n greater than log n square. Now, from this line, log n times log n greater than log n square, and log n times log n greater than 2 log n. Now cancel log n both sides, then log n greater than 2. That implies log n greater than e square. And from this expression that implies n greater than e to the power e square. So for n greater than e to the power e square, our inequality log to the power log n always greater than n square. So for this n, 1 over log to the power log n less than 1 over n square. And this is our given series. Now apply series both sides. Now by comparison test, since this series is convergent, therefore our given series is convergent. That means this series is convergent series. Okay. I hope my all viewers have understood in which type of series, which type of test would be applicable. Okay. Today I will stop here, and if you realize that this video is helpful, please click the like button and share with your friends, and of course subscribe my channel also. Thank you so much.